but it's very important material to have an underlying concept, or at least underlying understanding of. So it's worth going back to the pre-calc, talking about it, and then bringing it forth into the calc. All right. So the notation, cosine with a -1 as a power, seemingly as a power. It stands for inverse cosine. All right. So that's this. But we also noted as the arc cosine. They mean the same thing, at least in terms of how we approach problems. In terms of what they look like geometrically, not really. Not really. The arc cosine is really more of a measure around the arc of a circle. So it's more of a metric, whereas the inverse cosine is a graphic function. So they're basically talking about the same thing, but just looking at those two things in different ways. Being able to distinguish between the two is useful, but not essential. All right, same idea with the inverse sign versus the arc sign. Inverse and inverse arc. You also, I almost wrote should have learned, but I thought that would have been a little too snarky. But yeah, you also learned that inverse trig functions are restricted so that they can be functions. But we're going to go over it anyway. All right. So off on the side here, I'm just gonna chuck in there a traditional cosine function. And what I mean is cosine just on the interval of 0 to 2 pi. So 0 to 2 pi. Oh, that's not a 0. 0 to 2. And going from -1 to 1 for the y min and y max, because those are the parameters of a cosine function. That much at least everybody knows, because you don't get this far without knowing that, or at least having known that at some point. I hit the wrong thing. All right. So you don't need the full-blown graph, just a quick sketch of this, because all I'm going to do is talk about some points on here and how they relate to the inverse. Right, so up on the y-axis didn't show up, so let me just pop that in there. Actually, I'll accentuate it. Here's x, and here's y. All right, so we have some points along our cosine graph, important points, maximum, minimum points, roots. Those are the basic elements of a cosine or sine graph, and they also correspond with the quadrant angles or quadrantal angles on the unit circle. All right, so this one has a coordinate of 0, 1. This one has coordinates of pi over 2, comma 0. Purple, I think. This one has coordinates of pi, comma, -1. All right, there's more points beyond there, but we'll start with those. Inverses, we can think of inverse functions as reflections over the line y equals x, such that the function has an inverse function. All right. So what that's telling us, I mean, it's funky notation, but it's really just saying that I'm taking some function f of x, reflecting it over the line y equals x, the result of which will be another graph. That graph also needs to be a function. Functions, I mean, the simplest way to determine if something's a function is if it passes a vertical line test. All right, so you can make a note of that. I mean, not everything has to be in math symbolic notation. The inverse has to pass the vertical line test, the VLT. All right. So in order for the inverse to pass the vertical line test, the original function needs to pass the horizontal line test. All right, so that has to pass the horizontal line test, which works the same way as the vertical line test, just horizontal lines. All right, so this will come into play in a couple of seconds when I start graphing the inverse from this function. So in order to graph a reflection over the line y equals x, what we do is we switch the x and y in any coordinate. All right, switch the x and y in any coordinate. So my new coordinates would be 1, 0, 0 pi over 2, and negative 1 pi. Bottom line is we're looking at x values that would go from negative 1 to 1, and y values that would be in terms of pi. So I guess I'll go 2 tick marks up and call that pi. So I'll plot 1, 0, which would be right here. I'll plot 0 pi over 2, which would be right here. And then I'll plot negative 1 comma pi, which would be over here. All right. Now, the inevitable question would be, okay, well, there's more points on the cosine graph. In fact, infinitely many more points. What about this one over here at 3 pi over 2 comma 0? Well, if I were to do the switcherooski on that one, I'd end up with, I just put another tick mark here. I'd have another coordinate at this location, and then more coordinates over here, and then back over here, and so on. All right, so let's just play that out. I'm starting on my x-axis and drawing my curve. I get to this location here. The minute I pass that, the minute I make that turn, so this little sliver of nonsense that is actually going to help the cause, but it accidentally showed up because this terminal sucks. But that little bit of nonsense that showed up there causes this to not pass the vertical line test. Right? It hit 2 points. So it would not be a function beyond this location. So if I take any points beyond this location and plot its reverse, switching x with y, that's going to create something that's not a function. So all of these points would be irrelevant. So we don't want any of them. So I don't want any of this stuff. All I want are the coordinates on this tiny little sliver of an interval. All right? That is actually your arc cosine graph. That is the graph of y equals, I could write it as cosine with a little power of negative 1 of x, which is the same as arc cosine of x. All right? And it also gives us a sense of where these inequalities are coming from. Arc cosine is between 0 and pi. All right? Well, this is my arc cosine graph. Look at the y value. Yeah, it's between the x-axis and pi, between 0 and pi. Right? The other relationships are a little iffy, but they come from manipulating this green inequality. But we now know that arc cosine has to exist only between 0 and pi. Now, you may say, well, you chose that interval. What if I wanted to use this piece? This piece, if I just graph from here to here, I'd still have a fair amount of curve, and it would still pass the vertical line test. Why don't we use that? Just mathematically speaking, life is always going to be easier if you can incorporate 0 into whatever it is you're working on. So whatever interval I'm looking at, if I can have a 0 be part of it, that's a good thing. So if I had a choice between going from 0 to pi or pi to 2 pi, I want 0 to pi because 0 is in that set and 0 is a good number. All right. If I were to put this in my calculator, and actually just graph inverse cosine of x, second cosine of x. Zoom, I'll do zoom trig, zoom 7. It essentially gives you the same stuff, right? It's just a sliver of a graph. It's a little disconnected. It's not the best representation of it, but it's essentially the same thing, all right? And we'll talk about what we're going to use it for in a little bit. Now the sine function, sine of x. I'm going to do that over a wider interval. So let me just do a zoom 7. At a negative 2 pi to 2 pi interval. But I'm going to bring it in a little bit because I don't need to go out negative 4 to 4. Let me go negative 1 to 1. I just need a little bit more room to roam here. All right, so we can kind of use the lessons learned for arc cosine to help us figure out arc sine. And that goes back to what I was talking about notation-wise earlier, that reflection has to make your original function into a graph that's also a function. So your reflection has to pass the vertical line test also. If that's going to happen, then whatever points you choose in your original function need to pass the horizontal line test. That's another way I could have known not to go past pi. So once I get to this point here, if I include anything beyond pi, now I'm failing the horizontal line test. So what I want to do is choose a representative interval from my sine function that includes 0, because I like 0, that'll also pass the horizontal line test. So if I just live in this interval, I can get all the y values, all the values in a range, negative 1 to 1, also including 0. 0 is a nice number, and it's not going to fail the horizontal line test. There's no way, if I ignore everything else, if that green curve was the only curve that was on the graph, there's no way I would be able to draw a horizontal line through this in such a way that it would cross it more than once. All right? For a better look at it, maybe you say, well, that's distracting. I don't like it. So change your window to only go from negative pi over 2 to pi over 2. So this is a closer look at what that green curve is really representing. I think in this case it's easier to see that it's going to pass the horizontal line test for all values in this interval. There's no way I could draw a horizontal line such that it's going to hit more than once. All right, you could try it. It's not going to play out. I could snip this one in there too.
Oh, so for the reflection, it's a horizontal line test. You do that for the reflection, not for the original function.
You do the horizontal line test on the original function to determine what points to use for your reflection. Oh, need you guys too. There. I'll do a little color. Oh, a little mist, but that's all right. And a little arrow here to indicate that those are related. Okay, so now I just need some points. So I have a point right here. It has a y value negative 1 because it's the lowest part of a sine graph. The x value is negative pi over 2. And I have this one, which is the reason why I chose this interval, 0, 0. And then the remaining one, let's see, well, haven't used black in a while, pi over 2 comma 1. Okay. So the x values that are relevant here would be on the interval of negative pi over 2 to pi over 2. The domain of a function is equal to the range of the inverse and vice versa. So I now have a good justification for where this is coming from. So the y values for sine exist, the x values for sine exist between negative pi over 2 to pi over 2. So the y values for arc sine should exist on that same interval. All right, that's the relationship between inverse functions. It's like a mirror universe. Everything happens in reverse. All right. So my x values going from negative 1 to 1, just like the last one. My y values, let's see, negative pi over 2 to pi over 2. So there's really nothing more to it than that. I just put a negative pi over 2 here, a pi over 2 right here. Plot some points. I get a 0, 0. That should have been in red. I got a negative 1, comma, negative pi over 2. That's going to be in purple. Again, I'm plotting these points backwards. These points are getting plotted in the reverse order, but 0, 0. The same forwards and backwards. And then 1, comma, pi over 2 is going to put me right here. All right, so we're looking at something like... And so that's what your inverse sine function is going to look like. Which isn't too far removed from what the ordinary sine function looks like over a similar interval. Okay. So, some more pre-Calc type of stuff. See, we have arc sine of negative 1/2, arc cosine or inverse cosine of negative rad 2 over 2. That could be thought of as, just unit circle problems, saying, for example, what is the angle with a ratio of negative 1/2, specifically for the sine function. But we're restricting our unit circle to only focus on the relevant range, right? This range goes from negative pi over 2 to pi over 2. So if you think in terms of the unit circle, the good old ASTC, the 4 quadrants. Quadrant 1, 2, 3, and 4. The arc cosine function lives in the top half. So arc, I'll write cosine negative 1 of x, cosine negative 1 of x. The arc sine function lives in the first and fourth quadrants. Arc sine of x, inverse sine of x, inverse sine of x. All right, and that's just based on knowing what those terms of pi represent. It's the same as 180 degrees, so going from 0 to 180. It's the same as 90 degrees, so going from negative 90 to 90. So that's what's in the appropriate quadrant. What it does, it guarantees that we're going to get some positive ratios. We're going to have some positive ratios for sine and cosine, and we'll have some negative ratios for sine and cosine. Right? The result of all of these things give you reference angles. It's just a question of plot. So, if you know your unit circle stuff, then this is really no big deal. I'd be looking in the unit circle for the angle that has a sine that's equal to negative 1/2. But specifically in only the first and fourth quadrants. Well, everything's positive in the first quadrant, and I need a negative ratio. So now I've narrowed it down to the fourth quadrant. So what angle has a y value of negative 1/2 in the fourth quadrant? 330.
Why are we only looking at the first and fourth?
Because of this particular range. Okay, this is the same as saying negative 90, and this is 90. So that if you're going around your unit circle,
Oh, so it's for
right? It's
negative 90 is really 270.
Yeah. That looks too messy. So 330 degrees, we're living in a world of radians, so I need to know the radian equivalent of that.
11 pi over 6.
11 pi over 6. All right, so then the second question is saying, what's the angle that has a ratio of negative root 2 over 2? For cosine specifically. So it's got to be in the second quadrant, because again, everything's positive in the first quadrant. And my choices for cosine are only first and second quadrant. Right? That's this corresponding to this. So I need the x value in the second quadrant. That has to be equal to negative root 2 over 2. What's the angle that gives that? 135 degrees. Radian form 3 pi over 4. Oh, well, the ratio is negative. So negative root 2 over 2 is not related to these ranges. This is related to the domain of your inverse function, which exists between negative 1 and 1. So as long as negative root 2, whatever you're taking the arc sine or cosine of is between negative 1 and 1, you're good. The range, the angle that is a result, is what needs to be between 0 and pi. Now, there are some questions like the following that say that you could use your calculator. And you're like, oh, this is great. Calculator. I've grown to love that over the course of this semester. Arc tan, that's the same as inverse tan. All right, should be no problem. Look at that. Oh, beautiful. Check your mode. Make sure you're in radian mode, because the result of any of these inverse relationships should be an angle. All right, so if it's not an angle, well, then you did something wrong. But then also it needs to be specifically an angle in radian form. So it looks like we're in good shape here. So we got lucky. It won't always feel like you're getting lucky when you see a number like this, but you know, it's fine. So approximately negative 0.291 radians. All right, so, all right, that's great news. So let's try for inverse cosecant. Oh, there unfortunately is no inverse cosecant button on your calculator, but inverse, well, cosecant itself is a reciprocal of sine, so 1 over the inverse sine. Oh, is that the same thing? I wonder. So 1 divided by the inverse sine of negative 2.4. Hopefully you see why this is not going to work already, but if you don't, that's okay. Error domain. So error syntax means you type in something wrong. Error domain, error divided by 0, error imaginary. That could be you type something in wrong, or maybe the nature of the problem doesn't lend itself to a solution, aka something where the solution does not exist, passage or things like that. All right, so you can hit go to. Maybe you think, oh, I typed in something wrong, so I'll just take a quick look. No, I typed in everything correctly, so it should have worked, should have got an answer, but we didn't. Right, so then the question becomes, well, why didn't we? The answer is because the calculator is not perfect. Even though the inverse cosecant is something that does exist, the calculator can't get past the fact that you try typing in inverse sine of negative 2.4. The inverse sine function, the x values, have to be between negative 1 and 1. Same thing with inverse cosine. It's a no-go if it's anything beyond those values. Even though anything beyond negative 1 to 1 are perfectly fine for cosecant functions. They're not good for a sine function. So we have to make an adjustment, right? And the adjustment comes from intense college level calculus. No, it's simple Pythagorean theorem and SOHCAHTOA. I tried saving this before and it didn't work. Oh, because I didn't save. All right. This is supposed to be on the top of the next page, right? This little we can use implicit differentiation to derive business. Yeah? Yeah, I know, but it's supposed to be at the top, right? It doesn't make sense where it is. Because at the top of the page, there's no directions or anything, right? Yeah, okay. All right. So let me hold on to that. Get rid of that. I mean, this formatting thing should get, like, everybody in the class their typo bonus for the semester. Like, it just keeps coming up.
Just send you a message
on Remind. Page number, problem that had the mistake, and what I should do to fix it. Sometimes just telling me what the problem is. No. So, inverse cosecant of negative 2.4. We got to think about what that means for a second. In order to really think about what it means, we need to go back and actually talk about what it means to be inverse sine of something. All right? So I'm just going to kind of chuck it in here. If I have something like f of x is equal to the inverse sine of x, that x, I use the term ratio, but that could mean so many things. The ratios, when I talk about it in the context of trig, I'm talking about the ratios, the famous ones, the SO, the CA, and the TOA. All right? So this x is the ratio for sine, which is the O. All right? The most important trig functions in existence are sine, tangent, and secant, because those are the ones that don't have the cosine. Because the cosine is the complement of sine, the cotangent is the complement of tangent, and the cosecant is the complement of secant. If you know the three basic ones, then you can always figure out the other ones. The issue is they couldn't come up with a fun mnemonic device for sine, secant, and tangent. It would be unpronounceable, but so, ca, and cos, you could roll off the tongue for sine, cosine, and tangent, so let's just go with that. The key here is knowing that cosecant would have the reciprocal relationship. So this has to be the hypotenuse in a triangle over the opposite. All right? So, a really great thing happens. I can, and so my original suspicion was incorrect. I can do the whole secant becomes the inverse sine business. Oh, sorry, 1 over inverse sine. I don't know why I did that. It was so weird. 1 over the inverse sine. But I would also have to do it for the inner ratio, because that ratio, h over o, is the reverse of what I need it to be. So I can take the reciprocal of the function, but I also have to take the reciprocal of what's on the inside. Plus, and so at minimum now we at least get an answer, but it does turn out it's the correct answer. Negative 2.327 I'll go with. Now the questions that follow are things that, this is where we get the hit or miss territory. You may or may not have seen. Right? This stuff from what we just completed and up, you should have seen that before, but it might have been quite some time. Right? Now what we want to do is find the sine of the arc cosine of 4/5, and the sine of the arc cosine of that, and the secant of the arc tangent of 3. Right? The one way of really addressing the why as to what the reasoning behind doing this would be so that you can actually answer questions related to this when I ask you to find derivatives and antiderivatives. But the more important answer is that there are some algebraic situations out there that can be replaced with trigonometric expressions. And, you know, I mean, power rule is really nice. Finding derivatives of exponential functions and antiderivatives involving logs, they're not that bad, but there are some algebraic functions out there that are so not doable algebraically, but then once you convert them over into their trigonometric equivalents, then all of a sudden they become doable, and that's what we're going to learn about next class, but I need you to understand this stuff first.
I was going to ask for the derivative of those functions. Would it just be a regular chain rule?
It would be, except when I need you to put it as an algebraic expression, an algebraic fraction, so with no trig. So we need to be able to figure out how to convert from one form to another. Okay. So we start off by drawing a picture of some generic right triangle with some reference angle that we'll call theta. Now, up here, I said that when we have f of x equals the inverse sine of x, that x represented the ratio for sine, O over h. It's the same thing for our cosine. This 3 over 5 is adjacent over hypotenuse. So I have the adjacent, I have the hypotenuse. Well, what would be my missing side? 3, because that's one of those nice Pythagorean triples. Can't count on it all the time, but when it's there, it's nice. Right? If you don't like that, just use the Pythagorean theorem, you can figure it out. Right? But what I need, because this whole thing should result in some angle theta, I need the sine of theta. All right? It's weird notation, but basically what I'm getting at is the idea that I'm letting theta equal the arc cosine of 4/5, and then what I need is the sine of theta. All right? When you put it like that, they're composite functions, composition of functions. You're taking the arc cosine of 4/5 and replacing the theta with that. That's where this original expression comes from to begin with. All right, so the only recognition that needs to happen is that whatever this theta is, whatever the result of the arc, cosine, arc, tangent, whatever it is, that's going to be a reference angle in a reference triangle. So this theta is the same as this theta. So when I say find the sine of theta, I'm really saying find the sine in that triangle. All right, and since sine is opposite over hypotenuse, I have my opposite, I have my hypotenuse, because we're still talking about the same triangle. Honestly, why wouldn't we be? We've only drawn one triangle. The relevant ratio would be 3 over 5. Now this is something that the calculator will give you. You type in the sine of the arc cosine of 4/5, provided whatever you plug into the cosine function is within its domain, it gives it to you. But relying on the calculator here is not going to be useful for you because, yeah, okay, cool, it'll do pre-calc stuff for you. We need to learn from this so we can do some calculus. Okay, so we graduate to variables. So the sine of the arc cosine of x. So I want to come up with an algebraic expression that would represent the same thing as the sine of arc cosine of x. So let's draw another triangle. With a right angle. This guy here is our theta. And theta is represented by the entire triangle. This x is the ratio for cosine, which just like the last problem is adjacent over hypotenuse. All right, but this time it's just an x. All right, that's fine. I can write x as a fraction, x over 1. Right? Which makes my adjacent side x and my hypotenuse 1. All right, and a hypotenuse of 1 should not be unfamiliar. All the hypotenuses in the unit circle are equal to 1. Right? That's why it's a unit circle. I need to find the sine of this theta, which is the opposite side over the hypotenuse, just like the last one. It's just a little harder to come by the opposite side in this problem, right? Let me highlight that actually because it looks terrible the way I just did it. All right, so a little Pythagorean theorem to help you figure out what the remaining side is. What would that be, by the way? Yeah, square root of 1 minus x squared. All right, so set up your Pythagorean theorem, put your information in, and just solve for the missing leg, and that's what you'll get. All right, so the sine of theta would be equal to my opposite side over my hypotenuse. I'll write it over 1, but the 1's going to go away. It's really at the bottom of the screen that this pen stops really functioning correctly. So what I just got from this is that the sine of the arc cosine of x can be thought of as the same thing, and I can even just pop it in up here, as the square root of 1 minus x squared. Something you could verify. Sine of the arc cosine of x. And then I type in the square root of a 1 minus an x squared. I'm going to, because this is the older 84, it's not color screen, I'm going to just put, I'm going to hit enter on the slashy thing on the left-hand side. Just so it comes in as bold. Allows me to distinguish one from the other. Alright, so let's see. Let's do a zoom 6. Happened too quickly. Alright, let me bring it in. Maybe like -3 to 3 all around. There's one. There's the other. Alright, so they're both equations for semicircles. And you know, like if you write this as y equals and square both sides, you would actually get the unit circle. This is an alternative way of representing the unit circle function. Okay? But when we get into Calc 3 stuff next semester, Tuesdays and Thursdays, from 6 to 8, I believe. So, and I'll double check, but geometry on Wednesdays, once a week from 6 to 9. When you plug it into the Pythagorean theorem, so a squared
plus b squared.
Oh, the one is where the C would be, right?
Exactly.
Okay.
No, don't apologize. Right. And so the last one, I mean, normally I'd say I'll put a star on it and let you do it, but it's different enough that it might be a little weird.
But anyway, the moral of the story here is now we have a way to interchange back and forth between a trigonometric expression and an algebraic expression. Now, the thought process was, okay, yeah, this is great. I can totally, very easily take the derivative of this. Yeah, cool. I'll just use the chain rule. That's wonderful. Do you know what the derivative of arc cosine of x is? The answer is something along those lines. All right, so you're at least in the right ballpark. It's -1 over the square root of 1 minus x squared. So if you knew that off the top of your head, then yeah, sure, go for this one. But doing the conversion over to this form, still chain rule, but much easier chain rule for the derivative. For the antiderivative, honestly, I don't have the slightest idea how I would get started with this. For this, I have an inkling. I have a few different ideas. I would try them all. Some of them we haven't learned yet, but I'd get there. I'd get there with the algebraic equivalent. All right, so being able to convert back and forth would be pretty useful. Secant of the arc tangent of 3x. So another triangle. I'm putting them all in the first quadrant because x could be anything, so I just choose to assume that it's positive. All right. So some theta that represents the arc tangent of 3x. All right. Tangent is the OA part of SOHCAHTOA. So I'm looking at a 3x over 1. So opposite side, adjacent side. And then from that, we can get our hypotenuse using the Pythagorean theorem, which would be what? 1 plus 9x squared, or 9x squared plus 1. All right. And so the secant of that theta is what I'm looking for. Secant is reciprocal of cosine. Cosine is adjacent over hypotenuse, so hypotenuse over adjacent. Hypotenuse adjacent. Which I'm just going to write as the 1 plus 9x squared. All right. So, we could take a look at this one too. I'll just look at the simplified form because this is going to be a pain to type in. This less so. The square root of 1 plus 9x squared. I think my current window should actually be all right. All right, so it looks like a parabola, but it's not. Because if I set it equal to y, I'd have to square it to get it into its standard form. This is actually the equation of the hyperbola. Right? And there's a whole world of trigonometry related to hyperbolic functions. So this is the foundation, whether it's in the trig form or the algebraic form, it's the foundation of unit circle trigonometry, circular trig. This is the foundation of something called hyperbolic trig, which is an area that we'll explore a little bit, but nothing too crazy in this course. It used to be we did a whole unit on it, and then it became like a day, then now it's like minutes. We just kind of phased it out and replaced it with other things. So, but yeah, there's a lot to that. But we can now, using trigonometry, represent conic sections, circles, hyperbolas, ellipses, even parabolas in terms of trigonometric functions. And there's a lot of stuff we can do with that because in Calc 3, when we start talking about polar functions, so we work in a completely different plane, we work in a polar graph grid instead of x and y, everything's trig based.
Right? So to have a function like y equals x is not as useful as having something like, I don't know, theta equals pi over 4, for example. All right, so that's kind of where it's going towards. You don't